conditioning system, which is HVAC system. It's heating, ventilation, and air conditioning system. Like I said, I'm faculty from the Mechanical Engineering Technology here at ODU. I'm the advisor of the Makerspace group. I'll explain to you in a second a little bit more about that. And I'm also advisor of Engineers Without Borders. Let me see. Cannot hear me. People cannot hear me.
Nope, you're good now. I can hear you. You're good.
I'm good now? All right, cool. Well, good things that what I was mentioning before is something that I said 2 weeks ago. So I'm the advisor of 3 different student organizations. One is the Makerspace, the other is Engineering Without Borders, and the other one is the Baja SAs. I'll explain to you more in a second. What are the things that I've done as an engineer, and what are the things that I like are fluid mechanics, of course, which is one of the classes that I teach, and the main topic of today's talk. For fluid mechanics, what the knowledge that I learned or that I know about fluid mechanics, I use it to design system like the one you see in the picture. That's a room full of pumps, and that's most likely to pump. Typically, it's not the only fluid, but typically it's water, and in this case, it should be water because of the colors of the pipes and all that. So we pump the water for different purposes. So I've done designs of that kind that you see in that picture. For a pump, you also need a pump for a swimming pool. Of course, if it is a small swimming pool, you don't need a pump. But if it is a bigger swimming pool, it's a big swimming pool, you need a pump to make sure the water goes back and forth, because you have to, you know that the water gets bad if it's stagnant for too long. So you know you're gonna get algae, things like that. So you have to recirculate the water many times. I was involved a long time ago in a project of designing a swimming pool a lot bigger than the one I'm showing in the picture. It was a nice project to be involved with. Another class that I teach is thermodynamics applications, and one of the things that we study in thermodynamics applications is this little piece of equipment. Yeah, it might not look familiar to you, but you've seen it, and you've seen it even though you don't know. But you haven't seen it the way it looks in the picture because you've seen it hidden in this part of for an airplane. That's a turbine. That's how the airplanes can be pushed to move. That doesn't make the airplane to fly. What makes the airplane to fly are the wings, and today I can explain a little bit more about that. But the turbine is responsible of moving the airplane forward, not to elevate, but to move the airplane forward. The concept that we study in thermodynamics are also important to design a car. Now, not all the pieces of the car, but specifically the engine. So we understand and we look at the engine, and we understand and we can improve the engine by using thermodynamic concepts. This is something that I have not been involved in designing a car or the engine of a car, but I know how it works. That doesn't mean I can fix my car, but I know how it works, and I know why my car got damaged or doesn't operate, but I don't know how to fix it. For that, we have to call the mechanics. In any case, now, sorry, I'm going backward. The other class I teach that I know of is heat transfer, and for heat transfer, we study all forms of the heat transfer, which are conduction, convection, and radiation. And those are the things what you see in the picture is the typical things that you see in your kitchen. And we do design all that. Those are daily equipment that we use in a daily basis, but we all design that. I mean, engineers are the ones to design that, on all those pieces of equipment. We also use concept of heat transfer to compute the amount of heat in the summertime, the amount of heat that goes into a house. That is the reason we need a air conditioning system, because if we don't have an air conditioning system, our house will get hotter and hotter and hotter, and will get hotter because all the heat coming from the outside to the inside. So it's going to start increasing its temperature. Now, if we don't want the temperature of our houses to increase, the best way to do so is by cooling the air. And we cool the air with air conditioning systems. But to select the air conditioning system, we must know how much heat is going into the house. So the air conditioning just remove the heat out of the house. And that's the type of thing that I teach in air conditioning system. That's the other class that I also teach. So I can select and design system like you see in this picture here, where you could see all the duct taking the cold air into the rooms and all that. This piece of equipment of an air conditioning is the condenser. Let me see, yeah, the condenser. It's the one that is outside the house. And the one that is inside the house that looks smaller than this but similar, it's called the evaporator. By the way, those are I think I mentioned that in my first talk. Those classes, those three classes on the top, fluid mechanics, thermodynamics, and heat transfer. If you ask any mechanical engineer what class was the most difficult one in your career, and they will tell you one of those three or the three of them. They are the most difficult ones in the opinion of most engineers. I say that they are not difficult. The problem is that they are different. They are different. The main problem, and I already said this in my previous talk, but I'm going to repeat it today so you don't forget. The problem with those type of classes, those type of courses, is that you're not prepared for them. Nobody talks to you about them until you get to college. It's different like classes like dynamics or static. In dynamics or static, the basis of those classes is the Newton's law. And most of you have heard and have dealt with Newton's law already. Of course, depending on the age, but most likely, most of you that are hearing me right now know about Newton's law, which is the sum of the forces is equal to mass times acceleration, that very important equation. So you're introduced to that equation from the very beginning, your high school times and all that, and you come to college to take classes like statics and dynamics that are based on that. So you feel comfortable with those concepts because you have heard about them. When you come to fluid mechanics and thermodynamics heat transfer, it's not that way. It's new. Nothing is similar. Perhaps fluid mechanics is similar in some sense to Newton's law because we even use Newton's law in fluid mechanics. As a matter of fact, today we're going to use Newton's law to talk about forces. See, if I'm teaching you about forces and Newton's law deals with forces, well, most likely we're going to be using Newton's law. And yes, we're going to use Newton's law today. Before going to the actual class, let me also tell you about what my students do here while getting trained to become engineers. So I advise three different organizations. One is the group leading the efforts in the makerspace at ODU. Another one is the Baja Car Club, and finally the Engineers Without Borders. Let me start with the makerspace. This is a space that we have it almost done. Everything is there. We're about to open. This is a new space where students are free to use all the equipment in there. They have drills, lathe, you name it. 3D printers, of course. This is just one small shot of the space, but the space is bigger than that because we have more. I should have taken other pictures in the other angle so you could see what we have. We have welding equipment. We have equipment to make things with wood, equipment to make things with metal. Like I said, 3D printers and all that. And what is special about this space and about this is that it is the students who run the show. I'm the advisor. I give them guidance, but they're the ones making the major decisions as long as, of course, I approve. The other one is the Baja car. In this case, the students do build that car that you see there. That's one of our cars. The latest one, no, not the latest one, because the latest one is not built yet because of the COVID-19. We had to stop the process of the progress of the project. But they built that car. Everything you see there, that was built by them. The only thing that they don't build on their own, of course, are the tires and the wheels of the wheels and the engine. Everything else was made by them. Everything else was made by them. And we designed the car. So it's an all-terrain car. So we could take the car to any type of terrain, and the whole thing is to design it such as it doesn't break, because that car we could be very brutal on that car sometimes. And then finally, the last but not least is my student from Engineers Without Borders. This is a special group that they are in charge of helping communities around the world, typically poor communities that they don't have resources to have a better life. And I can give you one example right now, which is the project that the students went to that location. They went to Guatemala. We're working on a project in Guatemala to help a community to design and build a water distribution system. Right now, the people from that village have to walk like a mile to get some clean water to bring it home. And they have to go every day or every 2 days. In this case, what we're doing is designing a system that will take the water from that location where they get the water to their houses. So there are two different systems that we're designing. One is a pump system. We're pumping the water from that creek where they're getting the water from. We're pumping it up to a elevated tank, and then from the elevated tank, the water goes to all the houses driven by gravity. There are about 200 houses. I think last time I said 145, but I got corrected by one of my students in the last few meetings. She told me that no, we are helping 200 houses in that community. All right. With that said, let's go into our class. But before that, I have one question, and that is, are there any differences in fluid mechanics courses or applications in aerospace engineering and mechanical engineering besides internal, mechanical and external aerospace? And which one is harder in your opinion? So, you want to answer that question? My son is helping me. He's a mechanical engineer. I'm proud of him. He got his degree last year, and he's doing his master's degree in aerospace. But he's a mechanical engineer now. He's doing his master's degree in aerospace. So you don't want to take that question?
I'm good.
Okay. There is no difference between one or the other. The difference is the application. Whatever you learn here, everything that I'm going to teach you today, for instance, is exactly as you would learn it in aerospace. It's the same thing. When it comes to fluid mechanics, when it comes to all those classes that I showed you before that I teach in this university, they're exactly the same. They're taught the same way. The difference is the application. That definitely, if I teach you fluid mechanics, and you are in a aerospace program, I will bring more about the conversation. I will bring a lot more into the conversation, the wind design, the airplane design, and all that. But the concepts, the bases are exactly the same. There is no major difference. And it doesn't make it any harder. It's the same. If we want to say that fluid mechanics is harder, I don't agree. I don't think it's hard. It's just different. That's a better way to define fluid mechanics. But if you want to use that word of being hard or not, no, it doesn't become any harder if you go into a mechanical engineering program or an aerospace engineering program. The second question I have is, what's the difference in fluid mechanics courses in undergrad and graduate program? And how hard is fluid mechanics course in grad level? Wow, that's a good question. Yes, it gets a lot more involved. Again, I don't want to use the word hard, but it gets a lot more involved. When you go into grad school, you are basically reviewing everything you learn at undergrad, but they're stepping up the volume. They're increasing the volume. They're using a lot more math. I guess the major difference is that when you go to grad school, you look into what you learned in undergrad, but with a lot more math, more differential equations. And now that you asked that question, let me go through the agenda and come back to that point about math. Because in my today's talk, we'll have some math. When you are an engineer, it's almost unavoidable not to deal with math. It's unavoidable. And like I mentioned a while ago in my last lecture, I don't need you to love math. I don't need you to love math. I just need you to hang in there when it comes to math. But math is necessary in engineering. Very, very important. It's necessary. Don't love it. That's fine. But and that doesn't mean that you could not become a good engineer. You could. You just have to hang in there. when it comes to math. And today it'll be a proof, because today I'm going to be talking about fluids and their properties. This is something that I already mentioned last time, but I wanted to review those concepts so it comes back, I refresh your memory. I'll talk about hydrodynamics and conservation of mass. There are many types of conservation when it comes to hydrodynamics, but today I'm going to focus only on conservation of mass. Then I'll talk about forces due to a moving fluid. I'm going to talk about the force equation, which I should have said right there, an extension of Newton's law, because right there, Newton's law will pop up. And then I'm going to apply that equation to a force, to study force in a vane due to a moving fluid. I'm going to give you explanation on why that's important and why we care about studying that, which at the end is what you're going to be doing in the homework assignment I'm going to give you at the end of the class. I'm going to let you run a virtual experimental work so you could compute the forces in a vane. More about that at the end. So, and at that, then point number 6, I'll talk about the difference between theoretical work and experimental work, and of course, based on the subject of forces due to moving fluid. Finally, I'll talk about the collecting and processing the data and the homework assignment. And as you could see in the little square below, I'm telling you, you will be involved today, you will be involved in activities typical that a typical college students are involved in or are involved with. So I'm going to teach you exactly how I teach my students here. I'm going to teach you using even the math that I deal with them. I tried, of course, to use the simplest math possible, so you follow my lead here. But I'm gonna take you into that experience. So that's why, if you don't understand anything, shoot me a question and I'll answer to you. It's very important. So let's start with fluids and properties, and what is a fluid? The formal definition of a fluid is a substance that continually deforms or flows under an applied shear stress regardless of the magnitude of the applied stress. Yes, I know, shear stress is an ugly word. You don't even know what it is, and that's fine. I don't want you to start thinking about shear stress right now, but that's the formal definition of what a fluid is. What is important about the shear stress, shear is this. It's when two things there is kind of a friction. When you get your hands and do this is shear, right? This is shear. I'm applying a force parallel to the area, parallel to this area, right? That's what shear stress is, or that's what shear stress is related to, okay? In a fluid, if I try to do this, that fluid will deform, and it would imply that it will move. If I try to apply this to a solid, basically nothing major happens. The solid still sit, doesn't move. So, but in fluid, if I apply shear stress, the fluid moves, as you see in the pictures right there. So in the pictures that you see, in the small videos that you see there, fluid is continuously being deformed, moving. There is shear stress. There is shear stress again, like I said before. When it comes to fluids, there are two types of fluids, and they are liquid and gases. Air, the air that you're breathing right now, that's a gas. And all the concepts that I'm going to teach you today apply to that gas as well, specifically today. However, when you take fluid mechanics class, the focus is on liquids only. Everything you are taught in a fluid mechanics class applies to liquids 100% sure. Now, they could be extended to gases, but you have to be careful, because depending on how fast the gas is moving, the theories that you learn, the physics that you learn when dealing with liquids might change, might be different. So be careful. If you take a fluid mechanics class, think in your head, fluid mechanics, liquids, fluid mechanics, liquids, but it might be extended for certain cases when gases are moving. Now, let me get into more on what the properties are. One of the very important properties of a fluid in general is pressure. Now, pressure, the definition of pressure is the one given by that equation. Pressure is force divided by area. Pressure is force divided by area. Now, every time there is a pressure in a fluid, that implies that fluid is capable and is giving you a force as a result. And the other way around as well. If I apply a force in a fluid, it implies that that fluid is experiencing a increase of pressure. The pressure can be explained better if we go into a molecular level. So think about the molecules that are moving in on the screen. Think about those molecules. Look at how they're moving and moving and moving nonstop. All right? And those molecules do change direction when they collide among each other, or when they collide with the walls of the space where the container, the space of the container. Now, the pressure, that pressure you see in that equation, is related to the amount of collisions of those molecules against the wall. So depending on how fast they collide with the wall, the pressure is higher. If I have a collision like this, a weak number of collisions, a small number of collisions, I have a pressure. But if I have a lot more, I have a higher pressure. Let me see, I have another question. Could plasma be considered as a fluid, and why? Yes, it could be considered as a fluid. You're right, I should modify my slides. Plasma is also a liquid. However, we don't study that fluid in fluid mechanics because there are other properties related to their electrical charge that are not that we don't deal with. So that's why when you deal with plasma, it has to be taken in another class. But yes, good question. I should have added that to my slide. It is a fluid, but it's a special fluid because it's based on electrons and all that in the charge, in the electrical charge, and that modifies on how it behaves. Good question. Very good question. So pressure is the amount of collision, right? So pressure is the amount of collision. It's colliding. It's the amount of collision of those molecules you see in the screen, on the screen right now. The higher the rate of collision, the more collisions I have per unit time, the higher the pressure is. And that's why I know, if I find a way to get that little box and make it smaller by squeezing it, applying force and squeezing it, since the space is smaller, there is the chances of those molecules to collide in a smaller space are higher. Therefore, the pressure increases. Similar thing goes as you might have heard in your high school. If I start heating up that space, the heat will increase the energy of those molecules, so the molecules tend to move faster at a higher velocity. And because I'm increasing the velocity, I'm also increasing the likelihood of those molecules to collide among each other and to collide against the walls of that container. So that's why when you increase the temperature, you would also see increase of pressure. So I need you to write down that equation because we're going to come back to that equation later today. Why? Because in that equation there is a term F, and that F is force. And as I said at the very beginning, I'll be talking to you about forces. So anything related to forces will come in this discussion. Another characteristic of the fluid pressure, and that's why I put this slide, is that about pressure, is that the pressure will always act perpendicular to an area. It doesn't act parallel. It acts perpendicular. It's exerted against the walls perpendicular to it, like in the pictures I'm showing you. So in this case, I have a cylinder with a movable lid, right? So I put a load on top of it. So because of that load produces pressure in the fluid, and the pressure will create that force against the lid. So that's why the load or the weight in that case will remain stationary at a point. Okay. Density is a property. It's a very common property that we study of any substance, but in the case of fluid, it's extremely important as well. And it tells you the amount of mass per unit volume. And basically this is related, going back to the idea of the molecules, this is related to the amount of molecules that you could find in a fixed amount of volume, okay? In a fixed volume. And that's what it is. How many molecules can fit in that space? The number of molecules that fit, if this is the space I'm talking about, the number of molecules that can fit here is different if I have air, as I have right now, or it is different if I have water, right? With water, I'll have a lot more molecules in that space. That's why the density of water is higher than the density of air. So, and what is weight? Weight is very related to that math, and it's related to the effect of the gravity that we live in, that we have on Earth, which is 9.81 meters per second square. And how do we compute that weight? And weight, by the way, is force. And the reason I'm introducing weight here is, once again, because it's a type of force, I'm going to have to use it at some point. So weight is equal to mass, the mass of that body, multiplied by gravity. Now, if I solve for mass here in this equation, I will have that mass is equals to density times volume. Okay? If I solve for mass here, I will get that mass is equal to density times volume. So since the mass is equal to density times volume, I will plug it in here. I will plug what mass is equal to, and I obtain this equation, which is density, weight is equal to density of the fluid, gravity times the volume of that particular fluid. And please write these equations down again, because we're going to use them later today. I have two more questions. Let me see. So Rami from Ecuador, how do you get density from the amount of moles? Because the moles is another way of defining mass. So you could, of course, in our daily life, with mass for us, we related to kilograms, and in your country, in Ecuador, is kilogram, but here in the United States, we use pounds. But they are equally related. They are related to each other. And there are constants that relate that mass to moles. And remember that moles, one mole is the number of Avogadro.
6.02.
6.02 tends to the 23, right?
Yeah, something.
I think is, yeah. What happens is that each of those molecules weight different, has different mass. So I could have one mole of air doesn't, okay, 6.022 tends to the 23 number of molecules one mole can have. Now, remember that's molecules, but we have to also consider the mass of those individual molecules. And that's also later. There are tables where they tell you what is the mass of one molecule of air. And that's how you could get the mass. So they are related, definitely. They are definitely related. The second question I have from Luis Angel Vergara, Hidalgo, Mexico. When temperature increases, could it affect on the density at a certain point? Yes, sir. It could affect. It will affect definitely. Now, it could affect weakly or strongly. If it is a gas, it will affect it very much. Very much. If it is a liquid, it will also affect it, but depending on how much of the temperature is, you could change it or not. See, this is what happens. When I increase the temperature of water, let's say I have water in a container. If I increase the temperature, see what happens is that the mass doesn't change, but the molecules, since they increase their kinetic energy, they have more velocity, they tend to separate between each other. And because they are separate from each other, the space they cover is higher, is larger. And because the space is larger, the volume is larger. So this is what happens on any substance. When you increase the temperature, the mass could remain constant, but the volume increases. Why? Because the molecules tend to be farther apart from each other. And because they're farther apart from each other, they will try to cover more space. By covering more space, you are effectively dropping the density because you're increasing the denominator here. And this is the type of explanation that could be easily be given if you look at the equations. And that's why in engineering equations, math is so important. The math is not there to make your life miserable. The reason we have the math in engineering is because it will help us to understand, like I just explained to you, what will be the effect of the temperature on a liquid or a gas. Now, once again, in a gas, if I increase its temperature of the gas, the molecules tend to move farther apart easier than when I have a liquid. When I have a liquid, the molecules tend to like to each other better. So when you increase the temperature, they'll tend to separate a little bit, but not a whole lot compared to if you were talking about a gas. Anyway, write down those equations because when I use them later on, let's continue. Let's talk about hydrodynamics. So let's make the fluid to move. So, but before that, let's talk about conservation of mass law. In engineering, not engineering, in any science, there is always a law, always a law. And the one that you're more familiar with is Newton's law. You're the law you have been a lot more familiar with is Newton's law. Now, today I'm going to talk to you about conservation of mass law. I'm going to try to explain in a funny way. But before I explain to you, I need to talk to you what mass flow rate is. Let me make that definition today. What is mass flow rate? First and foremost, we're going to use the letter M, and we're going to put a dot on top of it to refer it to mass flow rate. M without the dot is mass. But once I put M with a dot on top of it, we're going to call it mass flow rate. And what is that? But before I show you, I'll tell you that, let me show you this video because I want your brain to be thinking about what you see there. So let me explain to you what that is. This is an experiment that somebody made 40, 60 years ago. And all he had was a wire, all right? Was a wire. And then at some point along time, he started releasing some little droplets of hydrogen. Some little bubbles, sorry, shouldn't say, seriously, droplets. Little bubbles of hydrogen. So he released these little bubbles of hydrogen in a water moving from left to right, okay? And of course, because the gas because they were very, very tiny bubbles, those bubbles liked to follow the fluid, okay? Now, what I want you to see that is to keep that video in your mind and think about this. Let's start, let's wait for the start. Look at that. So this is time 0, 1 second, 2 seconds, 3 seconds, 4 seconds, right? As time goes on, the space that those little bubbles cover is larger and larger. So once again, let's go back. Let's see again the video in a second. So let's see, let's wait until start. That's time 0. 1 second, 2 seconds, 3 seconds. See, as when I said 1 second, the distance was up to here. When I said 2 seconds, then the distance covered was then here, then 3 seconds, then here. So it's moving, it's increasing the area or the volume that those bubbles cover is larger and larger as time goes on. And the amount of space those bubbles cover has to depend to the velocity of the fluid. The fluid is the one dragging those bubbles. So the velocity of the fluid and time will tell you how much space those little bubbles cover. So keep those concepts in mind. I have one other question. Let me answer that question. So, and this is from Taiwan. Does the dot on top of the M refer to the first order differential for mass? Yes, the answer is yes. It is M dot. No, I'll take it back. It depends. It depends on what you're referring to. No. The one that I'm going to explain to you in the next slide has nothing to do with the differential equation. It's just the definition of how fast a mass of fluid is moving. It's related to that. I'll show you in a second. It's related to the video you're looking at right now. However, in the conservation of mass law, what you claim shows up. I'll explain to you. Give me just five minutes so you can see what I'm saying. So, but in this case, the M dot is not a derivative. The M dot is not a derivative, and it's a great question because in certain books, in certain math subjects, when they put a dot, that implies a derivative with respect to time, but not in this case, not in this case. Good question. So anyway, keep in mind that the area those bubbles cover do depend on the velocity of the fluid and depends also on time. As I increase time, the area is larger and larger. Okay, now, what is mass flow rate? Let's talk about the flow in a pipe, inside a pipe. And that pipe is moving at a velocity v, lowercase v right here. And let's say I take a chronometer, right? And then same thing as I showed you in the video before, I have a wire releasing little bubbles of hydrogen right here, all right? And this shaded area is nothing but the volume. This little volume here is nothing but the volume that those bubbles, hydrogen bubbles, cover after 2 seconds. Let's say 2 seconds, okay? Mass flow rate, the m dot I'm talking about, mass flow rate is the rate of mass passing through an area. Mass flow rate is the rate of mass passing through that area, okay? So it's basically how much mass passed this area right here. Let's say where I told you I put my wire, this is the cross-sectional area of the pipe. So how much mass passed that area? Let's say this is kind of a door. So the question is, if you had a crowded space, not in these days with COVID-19, but if you had a crowded space with only one door, the mass flow rate of people passing through the door is what I want you to focus on, okay? Let's say I have this room is full with people. And then at some point, we open that door. The door in this space is in that direction. We open that door, right? What I call mass flow rate will be the mass of people passing that door. So I open the door, start my chronometer, 1 second, 2 seconds, 3, and I start counting 1, 2, 3, 4, how many people are leaving and so on and so forth. That idea of counting people is more or less the same thing here. But instead of dealing with people, we're dealing with mass. How much mass passed this door in 2 seconds, or in 3 seconds, or in 4 seconds? It doesn't matter. You fix the seconds. It doesn't matter. It could be 1, 2, 3, 4, 5. It doesn't matter. You will obtain the same result regardless of that. So mass flow rate is the rate of mass passing through that area. It's the rate of how much mass passed this door where I had the wire. Now, the equation for that, and yes, I'm gonna take you into math. Just be patient and ask me as many questions as you need. The equation of mass flow rate is mass per unit time. So how much mass I have in this shaded area, I plug it in here, and then divide it by the time. The 1 second, 2 seconds, or 3 seconds we talked about. If you decided to have 2 seconds, as I mentioned before, it'll be the amount of mass in this space divided by 2 seconds. That's what it's mass flow rate. And I have another question. Is mass flow rate kind of like electrical current? Yes, sir. It is very similar. It is very similar. If you think about it, electrical current is made of electrons moving, right? In a wire. It's the same idea. What happens there that the mass in electricity is the number of electrons, but it's the same idea. Same idea. Now, they're not exactly the same. They don't behave the same, but the idea behind it is like you mentioned. Yeah. So anyway, this is my definition of mass flow rate. And as I said before, I'm gonna call it m dot. Now, I show you 10 minutes ago an equation where that mass shows up. And that is the density. Look at the equation I told you to write down. I told you write down the equation for density, and you wrote density is equal to mass divided by volume. Well, if I solve for mass in that equation, you will obtain that mass is equal to density times volume. And that's what I did. I substituted my definition, what I know is mass based on density. and I plug it in here. So far, the mass flow rate is density, volume, sorry. This is not the same. This is lowercase v, and this is capital case V. These are not the same. Be careful. This is volume, this is velocity, okay? So this is density times volume divided by delta T. Now, this volume right here is this volume, the shaded area, the shaded region. Now, that volume can be computed with that area, the cross-sectional area, times this distance. Now, but this distance, as I explained to you when I show you the video, has to be related to the velocity and has to be related to the time. It has to be related to the velocity and has to be related to the time, okay? But hold that thought for a second. Let me just for now substitute what I know volume is. Volume is equal to the area times delta V, this delta V, this delta L. Why did I say delta V? Delta L. So volume is area times delta L, or that little distance right there. So I'm going to plug it into the equation, and now remember what I was mentioning before, that this delta L must be related to the velocity of the fluid, on how fast that fluid is moving, and the time. And this is something that I explained when I was showing you the video. Anyway, if I plug this in here, and then this volume into here, I get this equation. I swear God is correct. Don't worry about it. Don't even try. It's correct. Now, notice that there is a delta T on top. There is a delta T in the bottom. They cancel each other, and this is what I ended up getting. That the mass flow rate is equal to density velocity times area. Density velocity times area. And please write this equation down. Write this equation down. That is the definition of mass flow rate. And the mass flow rate is the amount of mass of the fluid passing through an area. How much mass did I get passing through that door that I told you about? So mass flow rate is density velocity times area. Now, let's apply that knowledge. Now that I know that mass m dot is density, velocity, and area, let's apply that knowledge. And let's assume I have this experiment in my lab. I have an amount of water coming into the top of the tank, and I have water coming out at the bottom of the tank. So water coming in, water going out, water going in, water going out, okay? Now, what happens if the amount of water on the top going through the top is larger than the amount of water getting out? Think about it. What do you think it happens if the amount of water coming here, I don't know, with a hose in your house, in your garden, you have a container and you start filling it up with water, boom. But somehow you poke a hole at the bottom, and you could control the amount of water going out through that hole, perhaps with your finger. Well, by the way, your finger will act like a valve, all right? Will act like a valve. But let's say that's the experiment you're running in your house, which you could do it as soon as we finish here, and you'll see that everything we're explaining here is exactly what you see in your house. So what happens if I have a lot more water coming in than the water coming out? Well, what's going to happen is that this tank, or the container, will start filling it up. We'll start getting filled up, all right? Now, let's go to the other way. What happens if this flow rate is larger than this one? Well, what would happen is that this tank will start getting emptied. You'll have less amount of water contained in the tank, less and less and less. And it will change with time, right? The level, this water level, will start decreasing and decreasing. It will change with time. At 1 second, at 0 second will be here, then 1 second, 2 seconds, 3 seconds, 4 seconds, and so on and so forth. So the amount of mass stored in this tank changes with time if these two are different. If this is larger than this one, then that level will increase up and up and up and up. And it increases with time. And if this one on the right is larger, then this level will reduce, will get lower and lower and lower, again, with time. And if those two are equal, what if m dot in is equal to m dot out? If these two are equal, then nothing will happen to the stored mass. It will remain the same. If I had 3 gallons of water, I will keep 3 gallons of water the whole time as long as m dot in is equal to m dot out. If they are equal, the amount of liquid or water in this case, if we want to, remains the same. The only way to change is by making these two different. If I make this larger, it increases. If I make this one larger, it reduces. So I can say by observation, because that's something that I cannot prove to you mathematically, but by observation, that if I subtract m dot in minus m dot out, that has to be to the rate of change of mass in the tank. This is what we call the rate of change. This in math, when you get to college, you're gonna call this a derivative. This is the derivative. Of course, I use another nomenclature to make it simpler, but this is basically the derivative of the mass with respect to time. So going back to the question I was asked 5 minutes ago, as you could see, there is certain relationship between m dot and that derivative you were talking about. There is certain relation, but they're not one-to-one. They are related through the conservation of mass law. That right there, my friends, is the conservation of mass law. And it's a law that we come up with just because based on observation. We see and we write in an equation what we see. Notice that if m dot in is equal to m dot out, the left-hand side becomes 0. The left-hand side becomes 0. What does that mean? It means that the change of the mass in the tank with respect to time becomes 0. That means that there is no change in the mass, meaning that that level is not increasing, neither reducing. It becomes 0. Now, what is interesting is that this conservation of mass, I just explained it to you based on hydrodynamics and the fluid mechanics, the fluid going into a tank and so on, but it applies to everything. It applies to many, many things. Let me show you one example. What if you decide to eat 10 burgers like the one in the picture? Huge one. They look yummy. Would you like to eat one more? That's huge. What if you try to eat 10 burgers of that one? Let me apply conservation of mass law. Let me apply conservation of mass law. And let me tell you, well, if I don't gain weight after I ate 10 burgers, it's because m dot in is equal to m dot out. That's the only way. The only way for you not to gain weight after eating 10 burgers of that kind is because whatever came in, it has to go out. Now, how did it go out? It has to go out. It has to go the way you're thinking right now. In the different ways we, as a human being, put stuff out of our body. I'm gonna let your imagination to think about that, but it has to be whatever goes in, it has to go out. Whatever goes in, it has to go out, because if not, then you'll be gaining weight. Okay? So what if I do gain weight? like you will if you do that, because it's not possible to get those 10 burgers out of your system that easy. If you do gain weight, that means that this right-hand term is positive. Is positive, right? And there you go. What we're trying to do here, or what I'm trying to do here, is to give meaning to the math, to the real deal, to what you see in real life. So the MDT, delta M divided delta T, is larger than 0. It's larger, and that implies that you gain weight. So now you could tell your family when you have a huge gathering, hopefully after COVID-19, of course, like here in Thanksgiving time. In the United States, we celebrate Thanksgiving at the end of November. So at the end of November, we are basically having a delta M over delta T more than 0. That's basically what we're doing. Gaining weight implies mathematically, that the amount of mass in your body is increasing with time. So that's why it's positive. Delta M over delta T is more than 0. Now, let me go to the other side. What if I do lose weight after eating those 10 burgers? That's basically impossible, but let's talk about that concept mathematically. If we lose weight, it's because our delta M over delta T is less than 0. It's negative. Why? Because my mass is reducing. If I lose weight, it's because if I weigh today, I didn't weigh myself today, but I think my weight was 205, I think. My wife will be proud of that. 205 pounds. So if tomorrow my weight is 200, delta M is 200 minus 205, which is minus 5 pounds. I lost 5 pounds. I wish. Well, who knows, at some day. 5 pounds in a day is impossible. But anyway, that's what it means, that I lost weight. I'm reducing my mass. And you could do that by doing this. I don't know, in the United States, there was a show, I think that show they got canceled, but that show came back a few weeks ago, in which they put a lot of contestants to lose, that are heavy, to lose some weight, but through exercise. See, what happened is that mass that you have stored in your body can be eliminated by doing exercise. So that the mass that you lose due to exercise will be like an M dot out, all right? Let me clarify, I'm clarifying. I just put that note so I don't forget to tell you that we need to clarify that when we're eating not to gain weight. That's not the purpose, right? What we're eating is to provide energy to our body. So in our body, there are chemical reactions that convert that mass of burger into energy that our body could use. Now, that's another way of aim that out. It's not going to get out of your system as you get things out in the bathroom, but it gets out into the system, into digestive system, because it went through the form of energy. All right. In fluid mechanics, most of the time, we assume that we study things in a steady state. That means that things are not changing with time. Okay. So my mass will remain my mass the same way today, tomorrow, next year, and in 10 years. So because of that, the right-hand side of the equation of the conservation of mass law becomes 0, and we ended up getting that in fluid mechanics, the way we study fluid mechanics is that anything that goes in has to go out. Like if you eat 10 burgers, those 10 burgers got to go out. It doesn't matter how, but they have to get out of your system. Otherwise, you gain weight. In our fluid mechanics, we're assuming we're not gaining weight, neither losing. Okay. Now, this is a long conversation, just because I need you to learn what M dot is, and I need you to learn that mass never changes. That mass flow rate never changes. If I see fluid coming into one side of a pipe, the amount of fluid coming in on one side of the pipe must be the same as the amount of fluid coming out of the other end of the pipe. It has to be. And don't get confused by the fact that you're adding molecules to this side. Well, these molecules that you introduced are not going to leave the pipe immediately, but other molecules on the other side will leave, such as the number of molecules in your pipe will remain the same. So if I had a pipe from, I don't know, let me pick a country, from Mexico. If I'm sending water from Mexico to Venezuela, my home country, from Mexico to Venezuela, somehow, I don't know why, but I'm just making things up. I'm sending water from Mexico. I'm pumping water from Mexico to Venezuela. If I'm pumping water from Mexico, if I pump 10 kilograms per second of water from Mexico to Venezuela, Venezuela will get 10 kilograms of water per second. They have to, if everything is in a steady state. And if anything changes in Mexico, if somehow Mexico decides to close the valve, well, Venezuela will see a reduction. Even though they are so far away, you will see a reduction. Not immediately, but very fast. In less than an hour, you'll see a change in a long distance. Anyway, the message that I need you to remember on what I just explained is that m dot is equal to density times velocity times area. And I told you to please write down that equation. And you also have to remember that the mass flow rate going into something has to be equal to the mass flow rate going out. It has to be equal. It has to be equal because there must be conservation of mass. Now, let's study forces due to moving fluids. Now with that background, let's study forces due to moving fluids. But before I do that, let me answer a question from Nakul from India. Why do we use that changing? Why do we assume that the changing mass is zero in fluid mechanics? Because it's simpler. I'm kidding. It is simpler. It's definitely simpler. The reason we do so is because most of the time that's what happens. When you take this class, fluid mechanics class in your college, they're gonna tell you steady state, and we're gonna assume that the mass doesn't change with time. They're gonna tell you that. Now, if you're gonna learn on how to deal with a fluid that changes with time, then you have to take another class, which typically is either a senior elective, or you have to take a master's degree or PhD degree to learn about that. But the fact that we don't cover those concepts in the undergrad doesn't mean we're not telling you the whole story. What happened is that most of the time, everything on Earth is a steady state. Go to any plant, go to any industry, and that industry is running 24 hours, 7 days a week for most of the days in the year. So it's basically a steady state. Now, if the plant stopped for maintenance, yes, when you go to maintenance, when you turn off a pump, then those little seconds that takes for the pump to stop and the water to settle, that's unsteady. That you will see changes in flow rate, you will see changes in forces and all that. But when we design as engineers, I don't design when I turn off the pump. Neither I design when I turn on the pump. So let's say I do my maintenance in the plant, right? And then I turn on the pump, the water start moving into the pipes that should be filled with air at that moment because it was emptied to make some repairs. So I'm pushing air. I wait for an hour. And once I wait for an hour, 2 hours, 3 hours, that everything is filled with water or filled with liquid in general, then from this point on, the system is steady, it's not changing with time. You will see the fluid moving, but the amount of fluid moving at that specific location will remain the same, doesn't change with time. Well, in engineering, you most of the time design for steady state cases. We do not design a system for when I turn off a pump, neither when I turn on the pump. We don't. We design for something that is steady most of the time. Now, be careful because there are few cases, very few cases, at which you have to design for that very beginning. And even though it will just take a couple of hours of a year, you will have to design for that case, because if not, pipes could get broken and all that. So be careful. It depends. But I would say 95% of the cases, engineering cases, things are basically steady state. So we don't need to think about the fact that mass is getting in or the pipe is getting filled or getting emptied. That's why we focus on that. And yes, what I said at the very beginning, I was joking, but it is true as well. It's simpler. It is simpler. I'm not going to lie to you. The math behind that is simpler. Now, let's focus into forces due to fluids. So what do we know so far? We know that pressure is equal to force divided by area. And we need that equation because force is there. And we're going to study forces. Then we learned that density is mass divided by volume. We learn about the weight. That weight is equal to density, volume times area, times gravity, sorry. We learn about mass flow rate, and the mass flow rate is density times velocity times area. And we also learn that the mass flow rate of the fluid going into a system has to be equal to the amount of water going out of that system. So those are the main concepts that I need you to remember. So it's going to be easier on us this second subject, this next subject, which is forces due to fluids. Now, why do I need to study that? Well, I need to know the forces. So another colleague of mine or myself as engineer can design this structure. For instance, if I have this river moving, as you could see them from the picture, it's amazing how this picture is very well taken, because even with the picture, you could feel the force, right? Kind of. You could see how that water is pushing against these structures right here. It's very important for us as engineers to determine the force applied on this structure by the fluid at this point. Why? Because I have to design that structure. As engineer, I have to design this structure, because if I make this structure weak, that water will just flush the whole structure. It will destroy the whole structure. So as a responsible engineer, I must find the forces acting upon the structures so I can design the structures. So that's why it's very important to understand and to study the forces due to a moving fluid because of that. Another example is a billboard. The many billboards you've seen on the streets or routes that you have seen in your life. Well, I need to know the forces acting upon that billboard so I can design this full structure so it can break. And what is the force acting upon that? The wind, which is air. And remember, air is a type of fluid. Is a type of fluid. So if the air flows into that billboard, it goes against that billboard will feel the force. But the question is not knowing whether I have force or not. It's given. We know there is a force. There is a force. The question is, how big is that force? Why do I need to know that force? Because depending on that force, this structure will be bigger or smaller. That's why I need those forces. And today I'm going to teach you how to compute those forces. So, another example. Let's say, and with this, I'm taking you little by little into the final homework I'm going to leave you to work on. So let's say I have a water jet, like the ones that you have coming out of your hose in your house. You have your garden hose, and you just open the water, and you see the water going out. And let's say I'm directing the water jet against on what we're going to call a vane. Okay, we're going to call that a vane. I'm going to give you more examples so you know what a vane in this case means. And that vane could be static, meaning I could be having it fixed, or I could let it move, okay? I could let it move. Now, if I'm gonna let it move, I'm gonna control that motion, so that motion could work to my advantage. Like in this case, a pinwheel. So each of these little things in the pinwheels are what we call a vane. And many of you might have already made these on your own when you were a kid, or right now. You don't need to be a kid to make that, right? And you already blow some air against the pinwheel and it starts moving. So why is it moving? Because this jet, well, in this case, it wouldn't be water, right? You're blowing air. You're blowing air. It wouldn't be water jet, it will be air jet. So that air jet produced by your mouth hits the vane, and because of the forces that jet produces, the vane gets moved. The vane gets moved. So we use it for the pinwheel, but listen, in this case, we blow air to make the pinwheel to move. Well, what if the pinwheel is moving with a motor? What if it is the other way around? If I made the pinwheel to move with my breath by blowing air, shouldn't I see something similar if I do it backward? Meaning that I move the pinwheel with a motor, and the pinwheel then produces motion, like in this case, like fans. In the two pictures you see in front of you, the fan and the pinwheel, the principles are exactly the same. The way I design my pinwheel so it moves, it must be, and the thought I put on designing my pinwheel to move must be the same ideas I have to have in mind when designing a fan. When designing a fan. And hey, there is a lot of engineering in a fan. It's such a simple artifact, but there is a lot of engineering behind that. A lot of it. A lot of it. So why are we studying forces due to moving fluids? So I can design better fans. Or so I can design better pinwheels. Well, I'm not going to design pinwheels as an engineer. So I can do that as a kid. Well, I don't need major knowledge to design my pinwheel, but I can design things like this. Or even better, like this. The blades of these wind turbines are vanes. And they're moving because the wind pushes, interacts with the blade or the vane, and it made it move. It makes it move. And it makes it move. And the same thing goes in, I don't know if you read the abstract of this talk. And I said that I was going to tell you, I'm going to teach you forces that are used to design turbines. But at the example I put, it went more than the wind turbines. I talk about the Hoover Dam. There are so many dams around the world to produce electricity. So we just create a huge dam or huge structure, a huge wall, so we could hold a lot of water. And then we grabbed that water and made it move through a pipe to heat a turbine. But in that case, a water turbine. Not of this kind. They're different, but the idea, exactly the same. They look different. The turbines, the wind turbines you see in front of you, they look very different to the turbines you would see in a dam. They're different. But the concept, the same. They are based on the same freaking concepts, the same thing. Now, where does everything start? It starts from Newton's equation, the same equation you've been dealing with for so many years already. And as I'm sure you're going to go for engineering or any science, you're going to keep dealing with that equation for a longer time. Get used to it. Now, that's the equation they gave us in high school. They said that Newton found that the forces, as a result of forces, I should have on an object of mass m, I will produce motion. I will accelerate that object. So he found that forces is equal to mass times acceleration. That's what he found. And for those of you that don't know what is on top of this letter, those are ways to denote a notation for something that we call vectors. I know some of you already know about that, but I know some of my dear participants here don't know what they are. It's a vector. Don't worry about that. It's just a mathematical way it's a mathematical notation that when you learn it, it will simplify your life. I have a question here from Luis again from Hidalgo, Mexico. Do fountains apply the same or a similar concept? Yes, because in the fountain, you need to have a pump, and the pump has to be designed with the same principles here. So anything that I'm going to teach you today is 100% related to a pump. Now, if you're referring to the part of the fountain where you see the water going up to the air and so on and so forth, well, since they are not hitting anything, there is no force related, because the forces I'm talking about is, if you look at my previous class and this class, the forces I'm talking about are the forces that appear once the fluid is in contact with a solid. Once a fluid is in contact with a fluid, regardless of whether the fluid is static or moving, is the forces that appear once there is a contact between the fluid and a solid. Now, when you made your comment on the fountain, if you're talking about the water jet going to the air and so on and so forth, no. Unless you have an object in the middle of the jet trajectory. What is the difference between force and momentum? Those are two concepts that are very well related to each other, because momentum is mass times velocity. They're related to each other. They're related to each other. As a matter of fact, now that you mentioned that, give me just 2 seconds to show you where the momentum shows up. I could have taught this class using the concept of momentum, but since I'm aware that many of you or some of you do not know about momentum, I prefer to stick to Newton's. And that's why I'm not going to mention the word momentum other than in 2 minutes, just because you asked that question. But they're related to each other. So I'm going to continue. I'm going to show you where the momentum shows up. Again, I could have explained this concept using momentum concepts, or momentum knowledge, but I prefer to stick to something that most people know, even from high school. Now, this equation, when you learn this equation, you apply this equation into the typical example in high school is a little car, right? Yeah, a car that is moving, blah, 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 so on and so forth. So if I apply a force to the little car, and then there are friction forces on the bottom and so on and so forth, that's where you apply that equation to. Now, the main difference between what you learn in high school and what you're about to learn here is that mass. Mass for the car is constant. It does not change. It's the same. You apply a force on that car, and the car doesn't change its mass. It's continuous, the same thing. Okay? In fluid, it's slightly different because I don't longer have a static mass. My mass is moving. And because of that difference, this term in the mass equation, in this term of mass in the Newton's equation must be treated differently. And this is how. So look at this. I am going to give the definition of acceleration. And acceleration is the rate of change of velocity with respect to time. And that's how you write it in mathematical form. Acceleration is change of velocity divided by change of time. Okay. So basically, how much the velocity changes as I go along in time. All right. So I need you to look at this equation right here. And I like you to tell yourself, what is mass divided by delta T? What is mass divided by delta T? Please note that when I multiply a term to a fraction, that term goes to the numerator, to the top part of the fraction. So basically, this is what I just circle in red, is mass divided by delta T. Look at the equation you wrote. Look at the equation that I told you to please write down. That right there is what we call m dot. That's mass flow rate. Well, Luis from Mexico, you were asking me about momentum. M dot times velocity is momentum. I wasn't planning on mentioning that because, like I said before, a lot of my participants here don't know about momentum yet, but that's momentum. And as you could see, they're hand to hand. They go hand to hand, hand by hand. Force and momentum are related to each other. So I need you to remember this equation and write that equation down. Forces is mass flow rate. The mass flow rate we learned when I explained to you the 10 burgers idea, yada, yada. So forces is mass flow rate times the change in velocity. Now, one thing that I wanted to mention about the change of velocity, in real life, I can change the velocity two ways. And that's related to the concept of vectors. But for those of you that don't know what a vector is, don't worry about it. Listen to this. I can change the velocity by changing its magnitude. So I could have my water moving at 10 meters per second, and then I can make my water to go 5 meters per second. And there are ways to do so. I'm not going to explain them to do today. I'm not going to explain to you that today because we only have a few hours. But the fact of the matter is that I could change the velocity of the fluid. There are ways that engineers have to change the velocity of the fluid. So I could have a 10 meters per second water moving and then 5 meters per second water moving down the road. So that is rate change of velocity. That is what it implies here. So this will be the 5 minus 10. So I always subtract whatever happens after to what happens earlier. 5 minus 10. So that'll be a negative change, right? 5 minus 10. 5 minus 10. But there is another way to change velocity, and that is that the motion could be in a horizontal plane, and then all of a sudden I can change the direction to a vertical plane. I could have 10 meters per second on one side, and then it changed direction to 10 meters per second as well. Didn't change the magnitude, but the direction changed. So I can change velocities by changing either magnitude or by changing the direction. And that's the key. And that is the key. If you find a way to change the magnitude of the velocity, you will have force. Look at that equation. If you find a way to change the magnitude of the velocity from 8 to 10, from 10 to 20 meters per second, you will have, as a result, a force. You will. But you could also find forces by changing the direction. And the change in the direction is the key on when designing wind turbines. What you're doing in the blade, what you're doing is changing the direction of the wind in the blade. At the moment the wind touches the blade, if you change the direction of the wind locally, you're not going to change the direction of the wind, of the whole mass of wind. It's the wind that's touching the blade. The wind that is touching the blade, when you change the direction, it produces forces. And that is what we do in the pinwheel and in the windmill and wind turbine. All we're doing is changing the direction. Not too much of the magnitude. It's changing the direction. I have another question from Rodrigo, Mexico City, and that how does this concept appears on the Coanda effect? I don't know what the Coanda effect is. Could you? Thank you. What is the Coanda effect? Interesting. But this Cool, man. I'm learning new things today. Thank you. But it doesn't seems to be, this seems to be more related to how the water prefer to stick to an object. And I would assume, I have never heard about this effect. Good. I would assume that it is surface tension what plays a role here. It is related because at the end what we're gonna do, I didn't know, I learned, you know what, shoot me an email at the end of this talk. I'm gonna give you my email, so shoot me an email so we could keep talking about this concept. But I haven't read about this effect, but it seems like it should be, based on what the pictures that I saw, it seems to be related to the to surface tension effect, which is another concept that I didn't want to touch upon today. Because of that force appears, what's going to happen is that it'll be one more term on the left-hand side. But I can keep talking to you later on. I don't want to deviate the class to this new concept that I'm not aware of, but it's very interesting. It's very interesting. One thing that I wanted to clarify. So that's a question that I wrote in my previous slide, but in reality, what I should have written is the sum of the forces. So because I could have more than one force. And indeed, we typically have more than one force. So sum of the forces is equal to mass times acceleration, meaning that the equation that I derived should be had written like sum of the forces equals to m dot times delta v. Another question, this time from Karen from Illinois. Is delta v basically the acceleration of the fluid? The answer is yes. If you have a change of velocity, there is an acceleration or deceleration, either one or the other. But yes, it's definitely related to acceleration. And if it is, then how is it equal to momentum if momentum is velocity times mass? Well, what happened is that the momentum, if the velocity is changing, so does the momentum. So acceleration and momentum are also related, because the acceleration, if there is acceleration, it means that the momentum could be changing for good or for bad, for higher or lower. Okay, that's how they're related. They're not the same, but they're related because the definition of acceleration is rate of change of velocity. And if you see a rate of change of velocity, you are also seeing a change of momentum. They're related. Okay, so going back to this, the force that we should have been written is the sum of the forces equal to mass flow rate, the one that I told you to write down the equation, density times velocity times area, times the change of velocity. And again, that change of velocity could be changed in its magnitude, or it could be changed in its direction. And regardless of what kind of change, there is an acceleration associated. If I change direction, there is an acceleration associated. If I change the magnitude, there is an acceleration or deceleration associated, always. Wow, good. More questions. What if the speed is constant? Well, if the speed is constant, you don't have a force due to this change. That doesn't mean there are not forces. There are other forces, but not due to change of velocity. When you do have a change of velocity, that gives you force. If you don't have a change of velocity, then you don't have a force due to that. You could have forces due to something else, but not due to the changes in velocity. Another one. Luis, sorry for lots of questions. That's okay. You could always ask any question. It makes the whole thing more enjoyable for me. So sorry for the question, but the topic is quite interesting. I know, right? It's interesting. I love it. I love it personally. So if we wanted to define force as a function or in function of momentum, would it be force momentum? Yes, sir. Yeah, that'll be it. Yeah. And of course, I cannot write your equation, but he said, basically he said it's the change of momentum, but you divide it by time. No, there is not. There shouldn't be time. It's the change of momentum, because m delta b is the change of momentum. M dot times b is momentum. So when I have a delta b, if I split up that delta into B2 minus B1, I'll have m dot B1 or m dot B2 minus m dot B1. Those two are momentums. So once they change, it gives you velocity. So it's the delta T is the one that is extra. You shouldn't have the delta T right there. What I was saying before. Okay, reinforcing the concept that if there is a change of velocity in magnitude or direction, force. If I don't have any of those changes, then I won't have force due to that, but that doesn't mean that you don't have forces of another kind, okay? You could, and you have, most likely. All right, now, the problem with that notation, the vector notation, is that it's vector. And a lot of, in my experience, I do use vector notation many times, but there is, at the moment when you're designing something, you cannot keep moving with vectors. You have to write that vector equation into an equation that you could handle better. And basically, that equation can be written into 3 equations, and those 3 equations are equations per the directions. As you might know, as many of you might know, and if you don't, well, let me just say it. As engineers or in science as well, since we have to write mathematical equations, we need to fix a coordinate system. And in this case, and there are different types of what we call coordinate system. And in this case, it's that coordinate system that we call coordinate system, Cartesian coordinate system. Now, the whole point of a Cartesian coordinate system, and you could see in the picture on your left, bottom left, that's kind of the corner in your house, in your room. That's kind of the corner in the room you're in. The whole point of a coordinate system is to be able to mathematically formulate locations. So that point P that you see on the screen, since I have my coordinate system X, Y, Z, I can say its location precisely. Definitely, you also have to tell the user of your information where your coordinate system is, because my coordinate system is that corner right there. And if I tell you the correct location of a point right here, I will tell you the distance in this direction, the distance in this direction, the distance in that direction, in the 3 coordinate systems. Now, if you are in Illinois, then your coordinate system is somewhere else, meaning that the distance from that coordinate system to my point here in Norfolk is different to the one I have. So that's why that every time you deal with this type of thing, you must tell your client, or you must tell your the person you're giving the results to, where your coordinate system is located. Now, but once we have the coordinate system, this vector equation can be written in its Cartesian form. See, this, as you can see, it's exactly the same equation, but now it's defined per direction. So now I care about the forces in the X direction, the forces in the Y direction, the forces in the Z direction, okay? And then the velocities in each of those directions, okay? And once again, we're gonna use those equations in 2 minutes, but those equations are based on a coordinate system. And since they are based on a coordinate system, I need to say where the coordinate system is. So let's apply this equation. Let me tell you what we do here at when you're studying fluid mechanics. Oh, very important. Don't forget about that equation. M dot is equal to density, velocity, area. This M dot is the same M dot you see here, the same one. It's the same one. And it's the same that has to be conserved, that doesn't change. That if I have 10 kilograms per second of water coming into a pipe, for instance, 10 kilograms per second of water have to leave on the other end. Okay, remember that? Okay, let's apply the force equation or the momentum equation, because now that Luis brought up the conversation, this is also the momentum equation. So let's apply those equations into an elbow. See, what happened is that when the water goes into this elbow where the flow turns, as you could imagine, that flow will push the elbow. And indeed, the elbow will feel a force, okay? It's being pushed. Now, because of another of the Newton's law, we know that that elbow will counteract because of the action-reaction law, Newton's law, right? Third law. The fluid goes in, it hits the wall of the elbow, and because of the elbow is feeling that force, the elbow will immediately go against the flow, okay? Go against the flow with the same magnitude. And that's what we're gonna call a reaction force, a reaction force. Now, let's apply those equations. That seems to be too complicated. Let's apply that to the elbow. And let me focus just on the elbow, but before that, let me put my Cartesian coordinates, right? My x, y. And see, the z, since I'm in a plane right here, I'm not gonna draw the third coordinate system. However, in the direction perpendicular to the screen, there is no major forces because the pipe won't move in this direction. The pipe will move in this direction and perhaps probably in the vertical direction. Well, not to up, it could come down, but not in this direction. That's why that I'm gonna eliminate the third equation. Why? Because I don't care. I know the forces, there is no net force in that direction. I know that. So now let me focus on the elbow. But listen, what I want you to focus is in the liquid. I don't want you to think about the elbow itself. I want you to think about the liquid inside the elbow. And let's say what you see right there is just the liquid, not the elbow, not the solid part of the elbow. It's just the liquid inside. And again, let's apply that. As you could see in the equation, I have bx2, bx1, by2. So that means that I need to define the velocity at the inlet and the velocity at the outlet. I need to define things. So I'm going to define my point 1 being the inlet and my point 2 being the outlet. And this 1 and this 2 are related to these sub-indices. Okay? So what I'm going to do here is to plug in the velocity, the magnitude of the velocity at point 2. What I'm going to do here is to plug in the magnitudes of the velocity at point 1. Okay. So I'm going to just write, just so I don't forget, the velocity 1, I'm going to call it B1, and the other one I'm going to call it B2, just for notation. Okay. Now, as many of you have heard I've learned when dealing with Newton's law, the first thing you do before applying to Newton's law is to use what we call a free body diagram. In a free body diagram, what we're trying to do is to put all the forces that the object you're studying feels. Okay, you're thinking, okay, let's see what are the forces that are acting on or upon the object. So remember the equation at the corner. Remember I told you write down that equation. Well, if the fluid is moving, better yet, if the fluid exists, if there is fluid, there must be pressure. There has to be pressure of the fluid in this pipe. There has to be pressure of the fluid near the inlet. There must be fluid pressure at the inlet. There must be fluid pressure here, everywhere. If there is a fluid, there are molecules. If there are molecules, there are pressure. There is pressure. Remember, pressure is related to those molecules bouncing. So as long as we have a fluid, there has to be a pressure. Could be low, could be high, but there must be pressure. And if there is pressure, there is force. So at these points, at the inlet and at the outlet, I have a pressure. If I have a pressure, I must have a force. So the pressure at 1 produces a force at 1. And I'm just solved for force here. Force at 1 is equal to pressure 1 times area 1. and similarly goes to this one. But now it's acting downward, and there is an opposite to the velocity. Why? Because it's acting upon a surface, hypothetical surface, I must say, but it's acting upon a surface. Remember that drawing that I gave you about the cylinder, that the pressure, the force due to pressure is always acting upon the area perpendicularly? So it's acting perpendicular here, but why is it opposing the direction of the velocity? Because my focus is on the fluid in the elbow, not on the fluid in the pipe. So that's why it's acting, those two forces are acting against the fluid that I'm looking at. The other force that I'm pretty sure you thought about it is weight. Because the amount of fluid in that elbow has a weight. And finally, the other force that exists is the one that I just described before, the reaction force. The one that the elbow exerts against the fluid because the fluid is hitting the elbow. But see, the problem with this R, the way I draw it, is that it goes in a direction that has nothing to do with my coordinate system. And since my equations are based on my coordinate system, I need to split that force into two forces. One that I'm going to call Rx, which is horizontal, and the one that I'm going to call Ry, which is vertical. And now I have all my forces. Now that I know all my forces, I can make use of my equation. And let's do it. So look at this. So what is Bx2? So this is the velocity at 2 right here, but its x component. As you could see, this velocity goes along the y direction. It does not have any value in the x direction, so it's not moving horizontally. B2 moves vertically, doesn't move horizontal. So, because it doesn't move horizontal, this guy has to be 0. Now, Bx1 though, as you could see, Bx1 is the velocity along the x direction at point 1. That is equal to B1. And that's what I did here, right? This is 0, and this is B1, the one that I defined earlier. And now let's look at the forces. What are the forces in the x direction? Meaning what are the forces that are horizontal in my picture? These are vertical, have nothing to do with that. Weight is vertical, have nothing to do with that. Ry is vertical, nothing. But Rx is horizontal, but please note that it's pointing against the x direction. And then P1 and A1. And then P1 and A1. So I have those two forces in the x direction, and this is what I do. P1, A1, positive, Rx, negative. Okay? And that ends up giving me this equation. That Rx, this Rx, has to be equal to the flow rate times the velocity of the fluid plus pressure 1A1. Does it make sense? Hell yes, it makes sense, because if I increase, imagine this, put this in your head. If I increase the amount of water going into the elbow, the more water I have, the more push. And therefore, the elbow has to react against that push. And if this pressure is higher, it's also a high force in that direction. Therefore, Rx has to be higher. I have another question. Jonathan from New York. Why is the fluid pressure F2P2A2 directly downward? But I tried to explain before, but again, it could have, listen, the pressure in a point, it goes in any direction. It goes, if this is my point, it goes this way, this way, this way, this way, this way. What happens is that I'm focusing on the fluid trapped in the elbow. I'm focusing on the fluid trapped in the elbow. I'm focusing just on that, okay? So assume like you are imaginarily cutting the pipe and leaving only the elbow, only the fluid in the elbow. Because of that, the pressure goes against the fluid trapped in the elbow. That's why it's in the opposite direction. All right, so now that I did my work for the X direction, I'm gonna do it for the Y direction. And in the Y direction, let's see. So BY2, 2 is this point, okay? And it's the velocity, the component in the vertical direction of the velocity. What happens to be that the velocity B2 is fully vertical, meaning that this BY2 is this B2 right here. And if I go for BY1, that's the vertical component of the velocity at point 1, but there is no vertical component, so this guy got to be 0. Zero, nada. Now let's look at the forces, and I have P2A2, okay, in the vertical, pointing downward, as I explained before. RY pointing upward because it's the elbow against the fluid. And then I have the weight. And that's what I do. I plug in those forces with their positive signs or negative sign, depending on the direction. Okay. So for RY, and this is what I get. Does it make sense? Yes, it makes sense. Because if the fluid somehow became heavier, if this W became larger, then RY has to increase because the elbow has to push against. Okay. Same thing goes with the M2, the same explanation I gave before. Now, let's try to summarize a little bit, but let me make one more modification, one little more modification. Let me use the equation for mass flow rate. So the equation for mass flow rate is equal to, is density velocity times area. Okay? Now, I'm going to solve for velocity in that equation. And I wanted to plug this velocity, this equation, into this velocity, and this is what I get. Think for a second, and you'll see that is correct. See, this m dot is in the numerator, sorry, goes here, multiplies this m dot, it becomes m dot square. Okay. And in the denominator, I have density times area, but I'm writing 1 because it's the area at point 1. And if I do similarly with RY, this is what I get. Okay? Now, this is how we use the force equation. And what we just did, that's what engineers do to design the wind turbines. Exactly that. Exactly that. The difference is that in the wind, the interaction between the wind and the blade in the wind turbine, the B1 and B2 are not changed 90 degrees because you're not going to see the wind blowing and changing direction 90 degrees. The changes are subtle, 20 degrees, 30 degrees at the most, but you won't see 90 degrees. You will see certain change, but not that much. And when you go for those angles, you have to use trigonometry here. But again, what I'm telling you here is what our engineers do when designing wind turbines. These concepts, exactly that. The only difference would be, another difference would be that the weight of the air is not relevant. So they tend to neglect this. And another one is that the pressures are the same. The pressures are the same. So because they are the same, they typically neglect that because it is not pressure what makes the wind blades to move. It is the change in direction in the velocity that makes the windmills or the wind turbines, the blades of the wind turbines to move. All right. Talking about the wind turbines, another application of what I just explained in an elbow is in the anemometer. You've seen that probably. Okay. And it's the same. I have a jet of air hitting that cup, okay, and making it move. So this is kind of a that. So it's kind of I have a jet, but in this case, I'm going to turn into water. Why? Because, and I'm going to start wrapping up right now because my time is almost up. But the water hits the cup, okay? When the water hits the cup, it moves around the cup, all right? So let me apply the same technique that I explained to you. Let me put the Cartesian coordinates, okay? So this velocity one of the jet, the water jet, does not necessarily have to be equal to V2, should not, is not. So I'm gonna apply that, but since the force is in the Y direction, I'm gonna just focus on that direction, the Y, so that's why I'm taking only one of the equations. So the only force here is Ry. I don't have pressure because it's open to the atmosphere, as I said before. I'm not going to consider weight either for the same reasoning that I said before. So I have Ry. Remember that the object is working against the fluid, so it's pointing downward. That's why it's negative. And this is the velocity at Y at 2 in the Y direction. This is V2, but see, it's pointing downward, so therefore it's negative. Minus V1, but then the negative comes because of the equation, but V1 is pointing upward, it's positive, so it remains like that. Now I use my knowledge of velocity equal to m dot divided by density, and this is what I get, my friends. So this is the area of the fluid right here and right here. That is that area, that little tiny area. And this area is this area right here. Keep that equation in your minds for a second. If I do the same thing, but instead of a hemispherical shape, I do it in a flat plate. In a flat plate, the water goes up, shoots, and then goes, change direction in 90 degrees, same thing. Ry is negative, same thing as before. But in this case, the difference is that the velocity at point 2, which will be the exit, the outlet, is fully horizontal. So it has no vertical component. That's why it becomes 0 here. And therefore, using the equation of velocity, I get that the Ry is m dot squared divided by density and area. And now, these equations are similar to the equations I showed you before. And summarizing, look at this. If it is a plate, the equation is Ry 1 over area, m dot squares over density. And the other one is the sum of the inverse of areas, m dot square over density. Now, one thing that I need you to see is basically the same equation. Now, what I need you to think, and this will take me to the little homework that I'd like you to work on. Note that the equations are similar, but they're different. Where is the difference? The difference is that this has 2 terms. And this one has 1 term multiplying m dot square over density. That means that for the same flow rate, if I have the same flow rate in this jet and the same flow rate in this jet, the hemisphere will feel the largest force. Why? Because this term will always be larger than this term. And let's assume for now, just for a sec, that this area 2 is equal to area 1. They are not the same, but let's assume they are the same. If they are the same, this becomes 2 times 1 over A2. So Ry for the hemispherical case could potentially be twice the force in a flat plate. Well, my friends, that's what I want you to look at in my experiment. In the virtual experiments, my very good friend, Professor Nathan Luke, prepared for you. That's what you're going to look at. You're going to experiment with a hemispherical shape vane, and you're going to do experiments with a flat plate vane. You're going to plot in Excel the force as a function of mass flow rate, and you will see that for a fixed mass flow rate, the hemispherical shape vane will give you larger force. That's what I need you to prove. I'm going to skip this because I'm running out of time. So I'm moving into the experiment. So as I said in my previous, also I have the similar slides on my previous talk. Theoretical work is pure mathematics. Sure. So you've been hearing from me math and math and math and math. And I know some of you hang in there. Thank you for hanging in there with the math. I know it could be a little bit heavy on math. That's the nature of this beast. But now we're going to prove it. In the experimental work, is in a laboratory. In theoretical work, it's pure mathematics, as you did. In the theoretical work, we predict how magnitudes will be based on a model. Those are the equations we derived. Whereas in the experimental, we get specific results corresponding to the specific case. Now, in these experiments that you're gonna look into, we're gonna determine analytically the parameters the force depend on. But you already saw that. The force on a vane do depend on mass flow rate and the areas. Oh, and the density. But since we're gonna deal with only water, that's a constant parameter. Okay. Now, in the experiments, we're gonna change those parameters with the flow rate, and you'll see how they affect the forces in the vane. The whole point of the lab is to confirm theories or equations that we will eventually use to design things. Like I said, the equation that I show you, your work, your job in your homework will be to prove experimentally that what we derive today in class is correct. And why do you want to do that? Because those equations are the equations you're going to use to design a wind turbine, for instance. Now, the setup looks like this. I'm going to let you go through the whole package we prepared. So when doing experimental work, one of the most important tasks is to collect the data, of course, and then you need to do that. In this experiment, we're going to change some parameters and see how that affects the force in a vane. Your main goal is to collect the information correctly. Interestingly, in this case, in this homework assignment, you will not be asked to run any calculation. You're just going to be asked to plug in the numbers in a spreadsheet and see the behavior of the force as a function of mass flow rate. Now, the data you're going to collect, you're going to insert in Excel. And the Excel spreadsheet is provided similarly to how I provided the Excel spreadsheet for my previous class. You'll see that there I added a couple of columns to help you in the calculation. So I saved you time on that one. And the results, you're gonna present the results in numerical and graphical formats. And this is what you're gonna do. You're gonna run these experiments, and this is a cartoon of the experiment. So go into the material on that to see how it looks like. This is the spreadsheet. This is how your spreadsheet look like. Please do not pay attention to this number sign div divided by 0. This is because the data is empty. There are two things you're going to collect from the experiment. It's the mass of water. You're going to see Professor Luke explaining on how to obtain the mass flow rate. The mass flow rate is obtained by collecting 15 liters of water. 15 liters of water. You're going to see that in the experiment, during your experiment. But what I need you to do is to find out the mass of 15 liters of water. Find out. Google it if you want to. Google it. And then plug that number here. 15 liters of water. I need you to plug here the mass of 15 liters of water. And why? Because that's the mass that you collect to measure the flow rate. That's how we measure flow rate. We measure flow rate by collecting water and taking a chronometer. So we start the chronometer, the timer, and you start collecting. 15 liters, you stop the clock. And that time, you divide the mass that you collected by that time, give you mass flow rate, okay? So you're gonna enter the data in the empty columns right here and right here. And of course, you have two different tables, one for the flat plate vane and the other one for hemispherical vane. Well, the equations to follow are these, and those are the equations that you would do by hand, but I made it, in this one, I made it simpler on you. I made it simpler on you because I just wanted to focus on the results rather than the process of getting the data. So for each of the data in the columns, in the Excel spreadsheet that I show you, you're supposed to compute that. You don't have to worry because I already did this in your spreadsheet, and those calculations are the ones that use in this column and in this column. There are equations right here behind those cells. And those equations are this one and this one, okay? Now, the Excel spreadsheet, you're going to go through all the experiments, plug in the data missing on the spreadsheet, on the tables in the spreadsheet. The Excel spreadsheet will give you two curves, okay? It will give you two curves. What I want you to do is to analyze those curves with respect to these equations and tell me whether those curves do make sense regarding these equations. Are they correct? Remember, we are expecting the case for the hemispherical shape, hemispherical vein to have larger forces for the same amount of mass flow rate. Is that true? Go ahead and do experimentally. That's what we're expecting, okay? And we are also expecting that as we increase the flow rate, the force should increase parabolically, following a parabola, because this is a polynomial of second order. Does that happen? Go and take a look. So your goal is to compare the behavior of the curve obtained experimental measurements to the behavior of the theoretical expression you have in front of you. Are they the same? Or at least are they similar? And what can you come? This homework assignment is not by any means imposed. You could do it up to you. I was happy to see that many of you work on the homework assignment that I gave you last time, and I gave a lot of feedback to many of you. I'm still giving some feedback to some of you, but feel free to work on that. To get there, you're gonna use this click, all right? And this is the one that we send you with an email, okay? If any of you does not have that email, please shoot me an email today to my email. Let me write my email right here. Where is it? Oh, come on. There you go. My email is oayala@odu.edu. Please email me so I can send you this link. When you click on that link, this is what you're going to see. Oh, sorry. This is what you're going to see. You're going to click on Fluids Lab Activities, then go into the folder for forces due to moving fluids. This right here, if you click, you will download the presentation that I just gave to you. Go over the concepts that Professor Luque explains here, but it's basically what he goes through is explaining the whole setup and explaining the physics behind, which I just did in my talk. Here, he explained a little bit about the lab. Now, the actual virtual lab activity can be watched by clicking here. Just follow the steps that are given. And the Excel spreadsheet that I talked to you about, you can be downloaded clicking on this link. Anyway, I hope you have fun. It was, again, a pleasure to have you in my class. This is my last one interacting with you guys. Feel free to contact me. Let me go back to my spreadsheet so you could see my email. Feel free to email me at any time. You know, many of you, the people that already contact me, they know that I answer. So go ahead and answer. I'll be so happy, so glad to answer any of your questions. Do you have any question here? No. All right. If there are no more questions, that's it. It was a pleasure giving you a little bit of my knowledge, a little bit of what I know, a little bit of what I love. It was a pleasure to have you. Shoot me an email at any time. Go and do the homework. Work on that. Have fun.